All right, okay, awesome. I can hear myself really loudly now. So, hey guys, my name is Hari Pachigola. I work as a data scientist for Autodesk. And today I want to be covering how embedding models work from more of an intuitive theoretical lens. All right, before I get started, one thing I want to mention is that as developers, it's really easy to use these models as black box tools. Right, you have a chunk of text, you send it to some embeddings endpoint, and you get a sequence of numbers called the embedding. You're able to store them in, say, a vector database, and it just so happens to be that similar chunks of text have similar embeddings as defined by some distance metric. And to be honest, for most of you to deliver value to your respective customers, it's not super necessary to be able to explain how exactly these embeddings are being created. But I come from the perspective that in knowing so, you get a better appreciation for not only the model, but the code that your end users are interacting with. So the way I plan to break this down is by answering 4 overall questions. All right, we'll first talk about what it actually means for a sequence of numbers to represent something. Then we'll go into talking about the dimensionality of embeddings, right? Why are embedding dimensions so high? And why can't we just increase the embedding dimension? One thing I want to preface with is that there are pretty simple answers that you can probably think of for these questions. But once again, my objective is to give you an intuitive reason, focusing more on the theory as to why the answers exist the way they do. And then towards the end, we're just going to talk about other types of embeddings. So jumping right into this, let's talk about text embeddings, right? Which has a very simple definition, which at a high level is a numeric representation of a piece of text. And this has existed for a while, well before the whole AI boom, if you think of something like ASCII, right? Take, for example, the phrase, "hey there," with that exclamation. You're able to represent this in some kind of numeric manner. And the reason being is because our computers don't necessarily understand the letter H, but they understand, quote unquote, the letter 72, okay? But there is obviously a clear problem here, and it's that this representation of "hey there" doesn't really take into account how you use the phrase in day-to-day life, right? For example, you wouldn't say "hey there" at a funeral, but you'd most likely say it when you're meeting someone for the first time. So to dive deeper into what I mean by representing something as numbers, let's take a step back and focus on a fundamental principle within deep learning. So over here, I have an image of a relatively simple model. It has as an input 10 nodes, and as an output 10 nodes as well, with 3 hidden layers. Now, I want to have you guys make an assumption about this model. Assume it's really good at the task you have it being trained on, right? So assume it's a model that's really good at taking an input and classifying it as one of 10 different outputs. Or maybe in a general sense, assume it's really good at taking a sequence of max length 10 and outputting the next token or the next word. In this case, your vocabulary size might just be 10 words, right? No matter what assumption you make, if this model is really good at the task at hand, then that means as values propagate throughout the network, those values are not random values, right? Take, for example, the values that are being propagated in this 3rd hidden layer. Clearly, those values mean something about the input because the output layer is able to give a very accurate prediction, right? So you can think of an embedding in general as some output of an intermediary layer within your overall network because those outputs or those values represent the input in a pretty accurate way because the model is working pretty well. Now, in most language tasks, a simple neural network like an ANN doesn't really suffice, which is why I want to change gears into talking about attention. Okay? So this paper by Google, you probably have heard of it, it's called Attention is All You Need, was released back in 2017. And the core operation within attention is the scaled dot product attention. Right? Just to read it out loud, it allows you to dynamically weigh the importance of different tokens in the input sequence when encoding each token's representation. And I want to break down that equation on the right-hand side here, right? Where you can see that attention is a function of 3 parameters, the query, key, and value matrices. This is my kind of horrible job in trying to depict what's going on, but one thing I want to make sure that you understand here before I dive deeper is what's the input and output of attention. The input is some embedding representation of the text, which we'll talk about soon, but the output is refined embeddings of that same text. All right? And that's the main thing I want you to understand here, even if you're not necessarily able to follow the intermediary steps. So to dive deeper, the main thing I want to explain here is if you have a model like an LLM that's really good at predicting the next word, the first thing you have to give it as an input is some sequence of text. In this case, my orange cat bit me on my blank. It could be bit me on my arm, bit me on my left hand, but whatever it is, the model is really good at predicting that next word. In fact, when it comes to training an LLM, which is outside of the scope of what I want to talk about, when you train an LLM, you first focus on having it predict the next word before it's a question and answer system. So the very first step is you need some numeric representation of these individual words. And that comes from something called the embedding matrix, which is a learned matrix. These are the weights of the models. And initially, you just pull the embedding from the embedding matrix. The embedding matrix has dimensions of the vocabulary size and the dimension itself. So say that your vocabulary size is 50,000 words in the English dictionary, for example. Then you just pull that embedding where each row represents one individual word. Now, initially, when you train an LLM, these will just be randomly initialized, but as you go through that training phase, those values will have more meaning. But what you want specifically is an embedding for this input text. And the way that happens is through the query, key, and value matrices. All right? These weights, which once again are trained, re-represent your embeddings in a way that allows the model to understand which words are important for other words. In this case, the word orange is saying something about the word cat. It's not really saying something about the word me. On the other hand, the word bit is saying something about the word cat and the word me. And that's what the query and key are trying to do. In general, the query represents what that word is looking for, and the key represents what that word can offer. In this case, the word orange can offer something to the word cat, whereas the word on or me doesn't really represent much or offer anything to the word on. And when I say offer, I'm talking about quantifying that attention value, which is what this attention map comes into. Overall, after some more weird math that goes on, you have these refined token embeddings, which once again, previously these were independent embeddings. The refined ones take into consideration the context of the other words around it to have a better and richer representation of the input text. There was a GitHub repo I found that I think does a really good job in helping you visualize what's happening behind the scenes. I have it linked at the last slide. Over here, you see that the input are vector embeddings, which is coming from the embedding matrix, right? Each row represents an embedding for a specific word. And then you convert this into a query, key, and value vector, which through this whole self-attention mechanism has some output. Now, through this output, you do some more math, and it's able to very accurately predict the next word, in this case, left. So what exactly is happening here, right? You have a model that's really good at predicting the next word, and through the intermediary values, these embeddings get transformed into a value that makes the output layer predict the accurate next word, which means that these intermediary values can be thought of as the embedding for the input text. Okay? So these values, like I said in the previous slide, are not random. They encode something about the input that allows the model to make its next prediction. So the embedding for these LLMs or these vectors can be thought of as just some output of an intermediary layer. And it tends to be that final layer. So for a lot of LLMs, in this case, say llama embeddings or SentenceBERT embeddings, it's just some concatenation, say average pooling, across all of those embeddings in that final layer. Okay? And the reason why this makes sense at a high level is because the model is really good at what it's doing. As a result, the intermediary values encode some meaning of the input, and the overall purpose of embeddings is to represent the input, in this case, text. So we just talked about why embeddings kind of function the way they do, but you've probably noticed that embeddings, I don't know why my AirPods are connected, you probably noticed that embeddings live in very high dimensional fields, right? In the previous GitHub repo, you saw that embeddings were 700 plus dimensions. A lot of embeddings in general, say OpenAI embeddings, are thousands of dimensions. So why does it make sense to have so many dimensions? Now, there is a pretty simple answer, and this comes down to one of the fundamental principles in deep learning, which is the model's capacity or expressive ability. Given a specific task, you want to make sure your model is complex enough to be able to capture the distribution of that task. All right? The human language is pretty complicated. As a result, you want a complicated model to address it. And this equation over here just formalizes it, where your model has specific parameters called theta, and you want to find the optimal values of those parameters such that the expected loss of your model is going to be as small as possible. That's essentially what that equation is saying, and hopefully that's not too hard to wrap your head around. But I want to dive a little bit deeper and introduce two topics that are seemingly different, but I'll tie it together towards the end. The first thing is, what does the embedding matrix really represent? Like I said, each row represents the embedding of a specific word in your vocabulary. And there's this common connotation that I've read in like different articles and videos that says that each individual column represents some human interpretable concept, right? You might have a column, say column 42, that represents gender, or you have another column that represents emotion. Now that's not exactly true, and the reason being is that these concepts are represented as directions, not as dimensions. So semantic properties like gender and emotion are typically encoded across many different dimensions, but they're not attributed to one specific column or dimension in your embedding matrix. I have an example of that in the bottom right, where a pretty typical example is saying like, oh, you have the vector for king, and you subtract from it the vector for queen. Or you have the vector for woman, and you subtract from it the vector for man. And those resulting vectors point in a direction that encodes the meaning for gender. Okay? But the main thing here to notice is that it's a direction, it's not a dimension. And that's a pretty common misconception that'll help you understand some later concepts here. The other thing I want to talk about is, what do I mean by the expressive power of an n-dimensional field? What even is an n-dimensional field? So to break this down, geometrically, n dimensions refers to how many vectors that can be placed in n dimensions, such that the angle between any two of these vectors is 90 degrees. So for example, in 3 dimensions, you can only have 3 vectors, such that the angle between any 3 of these is 90 degrees. And the reason why this is important, because orthogonal vectors, which is vectors that are 90 degrees apart, are linearly independent, which means that depending on how many orthogonal vectors you have in your dimensional field, you're able to represent seemingly different or distinct ideas. So say in the case of 2 dimensions, where there's only 2 orthogonal vectors, you can't have more than 2 independent directions, so unrelated words or concepts would have to have some overlap in 2 dimensions. But this is not actually true for higher dimensions, and that's what the graph on the right-hand side shows. What I did here to create this graph is I generated 1,000 random vectors in different dimensions, and I show a distribution of the different angles between all of these vectors in said dimension. What you'll notice here is that in 2 dimensions, there's a uniform distribution, meaning that most of the angles aren't really like populated in one specific area of the dimensional field. Whereas in higher dimensions, say 100 or 1,000 dimensions, you'll notice a really stark peak between 90 degrees, right? In general, in higher dimensions, many vectors are nearly orthogonal. And that's really important because as you have more orthogonal vectors, you're able to represent different ideas with little overlap. The human language has many different ideas, say king, or say royalty, human emotion, fruits. And if you want to represent these different ideas, you want to point them in different directions. In 2 dimensions, there's not that many directions to point to that are different from each other. There's only 2 really. But in higher dimensions, as I just showed, there are many different directions that don't overlap with each other that allows you to capture the differences in the human language. So with that said, why don't we just keep increasing the dimension size, right? I've just shown that you have more orthogonality in higher dimensions, so you can represent different concepts more. So why don't we just keep going? So the simple answer here is just due to some limitations with memory and computation, right? When you have a very high dimension, in this case, your embedding matrix is V by D. By increasing D, you're going to do more like computation with the query, key, and value matrices. You're going to just have to store all of these values. And these LLMs are pretty big to begin with. But even if that wasn't an issue, right, even if we had infinite resources, it still doesn't make sense to increase the value of the dimensions. The first concept to help understand this is the idea of overfitting, which is pretty common for most models, right? Like I said, you want to have the model have enough expressive capability of underlying your data's distribution. However, it tends to be that if you have too much expressive capability, you'll pick up on noise and nuances within your data that isn't true for overall data, that isn't true for like customer data, for example, the data that your customers use to like predict from your model. So while that is a good concept to help answer this question, let's just dive a little bit more into some intuitive like math behind it. And so there's 2 concepts I want to talk about here. The first one is rank. Rank is really important in linear algebra. Essentially what it states is that it is the number of linearly independent rows or columns within a matrix. Over here I have an example matrix, matrix A, and we say that column 3, for example, is linearly dependent if it can be reconstructed as a linear combination of other columns. So if column 3 is equal to 2 times column 1 plus 3 times column 2, and then you get column 3, that means column 3 is dependent. Essentially why that's important is because column 3 isn't really adding anything to our matrix, right? If you can just reconstruct it with a linear combination of other columns, column 3 doesn't mean anything for our matrix. So what does it mean when we apply this idea of rank to our embedding matrix? Right? Linearly independent rows mean words can be represented uniquely. That's what the objective is. But remember, I said that columns can't really be thought of as specific concepts. They're just general features within your embedding matrix. But it kind of turns out that when you focus on your language data, right, your training corpus of data is going to be limited. There's only a finite number of concepts, a finite number of English meaning within your training data. And that's what I'm going to refer to in my next topic as the intrinsic dimensionality. Like most things in the AI space, it's an overly complicated name for a simple concept, right? So intrinsic dimensionality, R, of a corpus of text represents the minimum number of independent dimensions needed to capture the meaningful structure and relationships within language data, right? So to kind of put a better example on this, say that you train an LLM only on the text of Harry Potter, nothing else, so only on Harry Potter text. The word evil in Harry Potter has a specific connotation with it, right? It's going to have this mystical, more gruesome connotation. On the other hand, the word evil has a different connotation when we talk about Winnie the Pooh, right? It has a more comical connotation, a more jovial one. But my point here is within the concept of Harry Potter, there's only X or R number of dimensions that you need to truly represent the text and the meaning behind the language of Harry Potter. And that's what I call R. When you increase D of your the dimensionality of your embeddings past this value R, every extra dimension is just going to pick up on noise or some redundant information that isn't really useful for the model to represent its training data. And just to prove that I'm not making this up, there was a study that was published last month actually, showing that it is a pretty active area of research called measuring intrinsic dimensions of token embeddings, where they have two common ideas: the intrinsic dimension and the extrinsic dimension. And essentially what they've shown is that even though embedding matrices live in very high spaces, the amount or the effective dimensionality, which is what ID is taking care of, is much lower. Right? So the amount of dimensions needed to describe the structure of your embeddings is actually much lower than what you would expect or what the actual dimensionality of your embeddings are. Essentially, the main conclusion you can draw from everything I said here is that your data has finite amount of concepts, hence it has a finite number of dimensions that can represent it. Even though it's hard to identify what that finite number is, in theory, if you go past that, you're just going to pick up on noise and redundancy. So to put everything back together, I just talked a lot about text embeddings. I'm not really going to touch image embeddings, but still the same overall concept. But there is just one key thing I want to say that I wasn't exactly correct on before. I said that an embedding can represent text in a sequence of numbers. But it's not just limited to text or images, right? An embedding is just a numerical representation of anything. And I quite literally mean anything. You can have embeddings for chairs. You can have embeddings for different types of raisins. You can have embeddings for types of glasses. Right? The reason why I say this is coming back to my original point. For as long as you have a model that's really good at a specific task, any of the intermediary values to an extent encode that input. And as a result, those intermediary values can be thought of as an embedding. When we looked at the transformer with the attention, those intermediary embeddings and pooling them together was the final embedding that you get when you make an embedding request. In general, say that you have a model that takes an image of a plant and accurately classifies it to being one of 10 different species of plant, then the output of, say, the third layer is a valid embedding for that image of a plant. So you can do RAG on plants by just looking at the output of some intermediary layer. So I talked about a lot in the past few minutes, but I didn't touch upon several concepts, which is tokenizing, positional encoding, and a lot more. But the resources here on the right not only help me make these slides, but I think they dive a lot more deeper into some of these concepts. So that's all I have for you guys today. If you have any questions, I'm gladly to take them.
Yes. Congrats.
Awesome.
Do we have questions for Harry? Yes?
Oh, okay. Sorry.
No worries, no worries.
I really like the presentation. I think you covered like the mathematical side really well for someone who does not have a huge background in mathematics. I'm curious about the text embeddings because you kind of like dove into text embeddings for just letters. How much research is placed into like image embeddings, or like, let's say we're dealing with plants or dealing with objects, like when you're thinking about creating these values, not just for text, like how are you dealing, what is the research look for that? Like how much time does that take? I'm just really curious.
Yeah, so over here I showed this as like just representing like a deep learning model, but every specific task has like more specialized models. So say for images, you have like convolutional neural networks. For language, you have transformers and attention. So that's kind of like where the research is going. How do you represent this different kind of data? What embeddings really are is kind of just like an output of being able to train a model that does this, right? So an output of being able to train a model that can predict the next word is, say, you're able to represent the input, because the network essentially has to represent the input to create that output. And so that's what an embedding really is. So I'm not sure if I'm exactly answering your question, but the research right now is like, how do we create more specialized models for specific tasks? And in the embedding, you can kind of think of as like some like +1 that comes out of that research.
Yeah, got it. Yeah. Most of the processing or like the research is done on like developing the layers and training the model.
Correct. I mean, there's a whole area of literature that I didn't even talk about, like how you actually train the model, how you come up with a good architecture. Just embeddings is a very small, like, I mean, it's really big in the LLM space, but it's a really small concept when it comes to the overall literature out there.
Okay. All right. Thank you.
Yes, of course.
More questions? Harry, I have one. Can you explain why orthogonality is important for embeddings?
Yeah, that was a kind of a difficult concept to explain. Essentially what I'm trying to get at is there's a lot of different ideas in human language, right? And orthogonal vectors point in different directions, right? So if you want to encompass different ideas in lower dimensions, there's not too many opposite directions in lower dimensions, right? Or there's not too many independent directions. So in higher dimensions with more orthogonality, you can represent concepts that are very different with very little overlap. In case like that didn't make sense, I'm sure you might have seen like you take OpenAI embeddings and you do some dimensionality reduction until you can visualize them in 3D or 2D. And you notice that when you do that, a lot of the points make sense, but some of them don't really make sense, right? And the reason being is because in 2 dimensions, it's hard to encompass meaning, whereas in higher dimensions, it is much easier to. And one of the many reasons why is because of this idea of orthogonality.
Cool.
Awesome.
More questions? Yeah?
Hey, great talk. I wonder if there's a way, a question for you, is there a way to calculate the intrinsic dimensionality, or is it just experimentation? And also related, I'm curious, do different languages have different dimensions, like numbers in terms of ID?
Yeah, I mean, so I can't speak like, I can't give you an exact answer. I'm still like not too knowledgeable on this field as that question would require me to be. But in general, yes, you can like empirically try to figure out the dimensionality of your data. There are a few R libraries that actually try to do that. In fact, the study that I showed here, give me a second. The study here actually proposes a method to do that and applies it to LoRa, which is a way of fine-tuning an LLM. That's the whole connection between rank and intrinsic dimensionality there, if you're curious. But to answer your second question on like different languages, yeah, like you can't just use like the embeddings of like it really depends on your training data. That's what I mean, right? The embeddings of the word like hello in English and the word hola in like Spanish is going to be different, right? And that's just because the Spanish language is constructed a lot differently than the English language. So you will need different embeddings for that, if that answers what you were trying to say. Oh, never mind, I did not answer what you were asking.
Sorry, I was more wondering if the number of dimensions is different across languages, because then that means the number of concepts in different languages are different.
Mm-hmm. So the reason why, like the answers to that is yes or no, it really depends on your training data. Remember when I was like, oh, if your training data is only Harry Potter, then yeah, you probably need smaller dimensions. If it is just like a much larger corpus of text, like kind of like what OpenAI did, literally everything on the internet, then yeah, your intrinsic dimensionality is going to be significantly larger. But it kind of turns out that you don't really need all of those dimensions to do a good representation of your language. And that's what this paper goes into. So yeah, with more languages, you might need more dimensions, you might not, depends on your training data.
Gotcha. I'll ask you more questions after.
Sounds good, sounds good.
Thank you.
Cool. More questions? Yes? Here.
Thank you. Hi, I'm Philippe.
Hey.
I have a question on these embeddings, and I've been playing with vector databases
Yeah.
and trying to do RAG and all that good stuff. And there seems to be that embedding step for your data to put it into the vector database. But one of the things I'm challenged by is like I want to use different LLMs, but do I ultimately have to choose the embedding that the LM depends on? And are they different? Can I find a way to use different LMs with just one vector database and one set of embeddings? It's like I'm trying to find a creative way where I'm not locked in, where I have to do another embedding, and put in the vector database for another LLM, and it gets
Correct.
more complex.
So if I'm understanding your question, you're pretty much saying, like, obviously you get a bunch of embeddings from different LLMs. You're asking, are you just limited to that LLM in particular?
Yeah, I mean, can I put basically one set of data in and have all LLMs be able to use and find that data in the vector database? Or because they use different embeddings, I'm stuck having to repeat the process and make the database way bigger and
Right.
not
So you're saying, like,
compatible?
can you just put in a bunch of OpenAI and, like,
Yeah, yeah.
Anthropic and, like, Llama embeddings
Yeah.
together? So in reality, not really, because one, the dimension sizes are different. Certain OpenAI embeddings are, like, 1,000 plus. I think Gemini embeddings are less than 1,000. So you can't really do that distance calculation when the dimensions are different. But suppose they were the same, right? I mean, there are studies that show that, like, even though the values of these embeddings are different, within their respective embedding spaces, they represent similar things. But it's not necessarily true that Gemini embeddings for hello is the same as OpenAI embeddings for hello. Because once again, it's a different training data set. It's a completely different architecture. They're closed source models, so it's hard to really speak about that. But because they're very different in terms of how they were trained and how the model is designed, you can't just take those two different types of embeddings and assume that, like, you can just have close text by that. So you would have to, like, partition your vector database,
Okay,
have one.
so if I want to do
open
RAG, I kind of have to choose the LLM
Correct.
that I'll be doing RAG with.
Yeah, and there's actually a lot of interesting articles on how to go about choosing the right embedding model, because certain models are better at embedding certain things than others, right? Because some models are really good at embedding code, others are really good at embedding, like, artistic, like, languages, things like that. So I would definitely urge you to, like, do research on what kind of model is best suited for the type of text you're trying to embed, and then go from there.
Awesome. Thanks.
Cool. No more questions?